My name is Lucian. I'm a staff engineer at Garmin. I don't write as much code as I would like to, but I'm still a software engineer at my core. And as a software engineer, I do have a problem with estimation. Every time I start a presentation, an article, or something, I just think, I don't have enough content to fill it up, and when I reach the end, I'm oh my god, I have too much content. I'm not sure how I can shrink it down. So 153 slides. That's my number for today, you can get all these slides by accessing this this URL. You can also get some more references and image copyrights from here. So this is a tale of two problems. One is complexity, one is concurrency. One is solved, one is not quite solved. And we put this together because the one that's solved can help the other problem being solved. Let's see how that can go. But first, let's look at the relevant timeline. So that's kind of the timeline from which we exist as a practice. It started in 44 with the first programming, first electronic digital programmable computer. Then in 58, John Tukey first used the word software. In 63, 64, Margaret Hamilton started to use the words, the phrase software engineering in informal context to differentiate it between hardware engineering. And then in 68, we have the NATO conference. And in there, we use the phrase software engineering for the first time in an official context. So that's what I would consider the birth of our industry. You can see that's a lot of stuff happening in a very short period of time. Let's look at the 2 decades, 60s and 70s. So in 66, Bohm Jacobini wrote a paper, Flow Diagrams, Turing Machines and Languages, only 2 formulation rules. And that is known for what we call today the structured programming theorem. Then in 68, Dijkstra wrote the famous paper, Go to Consider Harmful, which kind of set path of this structured programming to move forward. And then in 72, we have the structured programming book by Dijkstra, Hoare, and Dahl. And that kind of, I would say that would complete the work being done on structured programming. Not that we didn't discuss over that, but that kind of gives us a time frame in which the main ideas were developed. And I'm going to use these 3 points there. And please note that we have the structured programming book 10 years after we started to use software engineering informally, right? So it's a very short period of time. In the same period of time, actually before we are discussing about structured programming, in 65, Dijkstra wrote a paper, A Solution of All Problem in Concurrent Programming Control. And in that paper, he introduced 2 major things. Introduced concurrency, basically. That's the first paper who mentions concurrency, as far as I can tell. It also introduces the mutex, which is kind of the method that we still use today to solve a lot of concurrency needs. We're going to focus a lot on this part here. That's our relevant, because that's still quite an unsolved problem for us. And 57 years later, Anastasia Kazakova made a survey about C++ development frustrations, and concurrency safety ranked first. And you can pretty much see here that's a big difference from the other ones, right? So 57 years, we still haven't properly solved concurrency. We solved structured programming in less than 10 years, but we have not solved concurrency in 57 years, not in a way that's sustainable. What we are going to do in this talk is going to look at structured programming. We take some lessons from structured programming, and then we try to apply to the concurrency problem. and we'll arrive with what we call structure concurrency. And we are doing that by looking at the senders-receiver model, so P2300, that's proposed for C++ standardization. What should you expect from this talk? The general picture, the important things that model the landscape here, and the why. Why do we want to go in this direction? What you should not expect from this paper is, from this talk, is an introduction to senders receivers. There are better resources for that. See, for example, Eric Niebler's talk on CPPCon. And we're not going to deep dive into details. Actually, we will have a lot of slides with details, with code. We're just going to skim over them just to show the point, not necessarily focus on what specific parts of the code are doing. So this is the agenda for this talk. Start with structured programming, see what that means. We look at concurrency with threads. We look at concurrency with tasks. We look at what senders receivers proposal means, and then we look at structured concurrency to kind of put all this together. And then we'll have a section in which we show an example that structured concurrency pretty much handles the same goals as we've seen with structured programming and is not problematic anymore. If you do have questions, please post them into Q&A. I'll try to take them as we go, but if not, I'm going to take them at the end. So let's get started. Structured programming. What do we mean by structured programming? I tried to look at the sources that I previously mentioned, so the 2 articles plus the book, and the book seems to contain most of the points in that were made in the previous 2 papers, so I'm just going to focus more on the book. And out of that book, I'm extracting 5 important points, 5 principles that would make our programming to be structured as opposed to unstructured. First, abstractions as building blocks. Second, recursive decomposition of problems. The third, local reasoning. Fourth, single entry, single exit point. And fifth, soundness and completeness. And we are going to go over them one by one and just try to understand what they mean if we want to apply them to structured concurrency. So first, abstractions as building blocks. This is a map of the urban rail system. It kind of shows the whole world, but it's a very poor map of the world. It's a poor map of the railing system. You see a lot of straight lines. The continents are just out of proportion. But it's still a good map because it shows us the essential part. It's an abstraction. We keep the essential, we keep the main connections between different cities, and we drop the accidental parts. We drop the curvature of some of these lines, we drop the distances, we drop the shape of the land. We don't care about that when we look at the urban rail system map. In software, we use them a lot, and I'm going to have 2 examples here, just very basics. A variable. Probably we are not thinking very often of variable as an abstraction, but it is, and it's a very important abstraction. What do we keep? We keep the type. A variable always has a type, at least in languages like C++ and static languages, and it has the property of keeping one single value. That's what we keep when we say a variable. What we drop is the current value of that particular variable. So for example, in the code below, we have a while loop and we use I in there, and I keeps changing, but it doesn't matter. We can still reason about what that code does. It's not the best possible code, it's just some code that we can reason about. And we can understand it because we know that I has a type, in this case, an integer, and it keeps one single value at a time. Hope that makes sense. Another example, which is much more important for our discussion, is a function. What do we keep in a function? We keep its signature. We keep the fact that it has one entry and one exit point. And we keep the main idea. what we drop is the actual implementation details. And I use this main idea thing, which is a little bit confusing. And the point I'm trying to make is that we give a name to that thing and we summarize the semantics by giving that a name. And at least to me, I don't think I have a good proof of that, but at least to me, all the abstractions that have name are more valuable than the other abstractions. So a function is more important than a for loop because it can name stuff, so I can express more with a function than I can express with a for loop. That's an interesting topic to debate further, but let's not do it now. So here is one classic example of an abstraction, and it's a funny one. So Plato defined a man to be a fatherless biped. And then Diogenes comes along with a plucked chicken and said, behold, this is Plato's man. So its abstraction was not the best abstraction, but it tried to keep something. It kept the fact that it's a biped and it's featherless, probably because Plato's seen a lot of bipeds which have feathers. So that's how he defined its stuff. Abstractions are not perfect. They do not properly entail all the properties of that. It's just an abstraction. We keep stuff and we drop stuff. Why do we use abstractions? Because it helps our mind. It focuses us on the essential part, and we ignore the non-essential part. Studies show that we have a very small memory. We can keep up in memory something between 5 and 7 concurrent things, not more than that. You cannot remember. On average, you cannot remember something like 20 digits number, something like that, right? So focus is something that we need to be able to entertain stuff into our mind. In structured programming, we use abstractions basically for function and for data structures. I'm going to focus a lot in this talk about functions. Data structures are important too, but they're just not so relevant for our talk. So functions are really important here. We should always remember that. Second point, recursive decomposition, which is known as divide et impera. According to Dijkstra, and he has gone a great length to explain this in the structured programming book, we can build programs by doing the following things. We can recursively decompose the problems into parts, which are smaller and smaller. We can make one decision at a time. And to do that, to make that decision, we usually look at the local context. We don't think about the whole problem. In general, later decisions do not influence previous decisions. So if I made one big decision at the beginning that I'm going to split my problem in 3 parts, then later on, I'm not going to reconsider that. That's most of the time. Sometimes that's needed, but that's the general idea. And we will have a successful refinement. We start with something vague, and then we go in deeper and deeper, and then we try to refine it and get to the right meaning. That's the main proposition here. And actually, what Dijkstra does is transform a process that can be quadratic into a linear one. You can just go linearly and solve these problems. One example, let's look at the problem to print the first 1,000 prime numbers. That's the example that Dijkstra gave, but I'm just going to do it slightly different than Dijkstra did. So the first step, we want to have a function that just prints the first 1,000 prime numbers. And then we try to decompose that. The first step in decomposing is we just think, well, we should do 3 things. We should define an array, we should fill that array, and then we should print that array. That's our decomposition. Then at the second step, we refine this and we actually put something more concrete. We put an array definition, a function call to fill up the array, and another function call to print the array. And then at a later stage, we look at one of these steps and we try to go deeper. How do we fill this thing? Well, we have to do some kind of while. We have some way of increasing the value until we get the next prime number, and then we just put that into our table. And then we refine this, and that to-do got transformed into a do-while loop, and we're just going one increment at a time, which is inefficient. So we may want to reconsider that. And we're starting from 2, and then we just go on odd numbers. And you see here, I'm kind of making a decision that somehow invalidates one of my previous decisions. So there are some exceptions to this flow, but in general, I'm trying to just go deeper and not change the previous decisions. Step 6, we try to define what is prime. We have some notion of what that can be, and then we actually implement it. We implement it in terms of another function is divisor, and then we can actually implement this function as well, right? And finally, we have the print array function. So the point that I was trying to make here, and the same point that I tried to make many years back, is that we can take one big problem and decompose it into smaller parts, and we can work independently on that stuff. That's very, very powerful, right? We don't have to consider the whole thing at once. We're just focusing on smaller things. Local reasoning. That means nested scopes. It's structured programming that pushed us towards using nested scopes. Prior to that, programming languages would just have variables that are globals, and you change one variable, you would have to think all the other parts in the program in which you change something. So that breaks locality when you reason. And also you should think of it as an encapsulation of local concern. So if I'm looking at the block of code, then you should not be considering the whole program. And you can see that those 3 things have some overlap, but they're just somehow different point of views in which we can simplify the problem that we're trying to attack with our software. And let's look at a simple example here. It's quite a poor example, but just to illustrate the point. So we have 2 for loops. In both of them, we are using the same variable I, and yet it's still okay, and the code still functions, right? The nested loop, the nested for in there, is using a different I than the first for loop, and that's okay. That's an advancement from structured programming. Of course, don't do that in practice. It is not the most readable code. As I said, this also converges to focus. We should focus on one thing at a time. The more our context is limited, the more we can, the better we are at reasoning about that. If we look at the formula of how to reason these things, this is the well-known HOAR formula. We have preconditions, we have some instructions. Based on that, we have postconditions. If we're looking at the smaller scope, then the preconditions are kind of in that scope. So there are few preconditions we are looking at. Again, if we are looking at a smaller scope, the instructions in that scope are few. So there are not a lot of things. Therefore, with a limited set of inputs, the post conditions that we can obtain are limited. So it's really important for us to be able to draw conclusions of the code that we are looking at. The next one, single entry, single exit point. This is a little bit more contrived because people still debate today what this means and whether we should have multiple returns in a function or not. I think the main takeaway here is that a function should report to one single caller, single callee caller. And not to do a lot of crazy things. It should not do long jumps. And that's the core of Dijkstra's paper, Go to consider harmful. We should not have gotos because gotos exclude this single entry, single exit point. You're looking at a code, you're expecting it to finish in one place, but you may overlook a goto that just completely changes that and you exit through some other some other way. Why do we want to do that? Because it's easier for us to just consider everything to be the same. If everything has the same shape, it has one entry, one exit, then we can linearize the whole process. We can have linear reasoning. You can have step A, then step B, step C. Of course, there can be alternatives in those steps, but if you think the alternative, the if statement, as one single step, then you still have single entry, single exit point. And a more important point that Dijkstra makes is that both the code and the execution have the same flow. So if you start reading the code from top to bottom, it's similar to how the machine executes that from top to bottom. So you can go in the same way. You can much easier reason about the code. And doing that, you have this same shape for instructions, of function calls, for block of code, for alternative, for loops. They all look similar, so it's much easier to combine them. Please note, there's always some caveats here. So in C++, we say we have one exit point for a function, for a normal function, even if we have one single return into that. But that's not quite true. In most cases, we have at least 3 exit points. So we can return a value, we can throw an exception, and we can abort. Either we directly call abort or exit internally, or somebody else kills our thread, kills our application or whatever, right? So kind of everywhere, with some small exceptions, we have these 3 ways. But we still, when we see a function like sum here, we still think of it as one single exit point. Hope that makes sense. And the final point, soundness and completeness. So in order to use structured programming, it has to be both sound and complete. If we lack one of these, then probably we can't properly use it. It's just a partial use of it. So the soundness of things. Applying structured programming can lead to correct programs. That's because how instructions are put in there. The logic of combination leads you to soundness, and that's mainly guaranteed by the soundness of your programming language. And the completeness of that, that comes to the Bohm-Jakobini theorem that tells you that you can apply structured programming for all the programs. And that's this paper. That's the most important thing out of that paper. So in summary, structured programming is about these 5 things: abstractions as building blocks, recursive decomposition, local reasoning, single entry, single exit point, and soundness and completeness. They all have the point to make us easily reason about programs and make sure that we can write sound programs in all types of problems. So that's about structured programming. Do we have any questions so far? We're going to reuse all of these later on. Okay, no questions, then let's look at threads. How do we do concurrency with threads? So what are the primitives here? That's the most important thing. They are the threads, which can be of many types, we don't care. And they are the locks, mutexes, semaphores, whatever, we just call them locks. Those are the 2 primitives. What primitives are those? Are they named or unnamed primitives? They are unnamed. They do not work as functions. So when we look at the first point here, abstractions as building blocks, threads and locks are not good abstractions. They do not abstract concurrency code, similar to how functions abstract single-threaded code. They do not abstract concurrency concerns. They would only abstract the interactions between concurrent items. So the threads just have their own execution flow, and then the locks will just ensure us that we can communicate between those threads. We can't have building blocks to build more and more bigger things out of those. So they do not quite work in the same way as we would see functions for structured programming. Let's look at recursive decomposition. Into what? How can we decompose a concurrent application when we don't have the proper abstractions to do that? So this is not quite properly handled by threads and locks. Local reasoning, that's also not something that thread and locks make it possible, because by definition, by design, they have no local effects. Why do we put mutex or locks into one place? Because we want to protect interactions for that place with some other places in some other context, right? So by definition, the reasoning is not local. You have to think globally for that. The first time you put a lock, the first time you put an atomic looks like a lock, then you're bringing in the global effects in your code. Single entry, single exit point, this is not quite applicable here. I'm not sure how to position this principle with respect to threads and locks. Soundness and completeness. They are complete but not sound. And we know they are complete because all the concurrent applications that we want to build can be built on threads and locks, right? So they are complete. But they are unsound. And the reason why I'm saying they are unsound because we don't have a general strategy to build concurrent programs. And that's what this survey shows. Concurrency safety is the #1 frustration in the C++ community. Some other languages may have some better alternatives, but roughly, in general, the software industry has this problem with concurrency. So the bottom line is concurrency with threads structure. Well, no. For most of the points that we've made here, the answer is no. So concurrency with threads and locks is not structure. Let's look at concurrency with tasks. The primitives here in this model are the tasks. And if you see my last year talk on ACCU was mostly focusing on tasks, which I defined them as independent unit of work. And independent here is the key word because it brings some of the local reasoning. Last year, I tried to show that the task can lead us to build safe concurrent applications. This year, I'm going to move beyond that point and improve on that and just try to make things structured, not necessarily just safe and sound. So with tasks, we usually think about two models. We have the raw tasks model, which basically a task is just a function. And we have tasks with continuation. That's the thing that I discussed last year. You basically think of a task as a pair of two things, one action and then some other action that should be executed when the previous action completes. With the caveat that you can interject other things, even concurrent application of tasks in between your main work and your continuation. And by doing that, you're basically separating out the entry point and the exit point into a task. You have this nice separation that allows you to build more complex stuff. This thing that I'm showing, I'm not going to insist on that, but it feels a little bit more like a hack. And that's because the inner task needs to change itself, needs to change its continuation to inject work in itself. And the upper part, the color of that thing will not know how the task is actually continued. So raw tasks are just like functions, but if we put continuations there, we can represent larger concurrent parts. And I was arguing last year that you can represent kind of everything that's concurrent, you can represent with these tasks with continuations. Let's look at the raw tasks. Are they structured? Well, it's a partial. We have abstractions as building blocks, so tasks can do that to a certain degree. We have not met the recursive decomposition criterion because you cannot represent something that has multiple threads with tasks because raw tasks have only one thread. Local reasoning is true because functions have local reasoning. Single entry, single exit point, that is not. This is debatable whether it's true or not. The way I put the reason why I put not here is because you can't properly structure your application to have those kind of semantics. So you have to do other things to get to this criterion. And soundness and completeness, that is true. The general takeaway here is that this is not quite structured. If we look at tasks with continuation, we still see a partial answer here, but for different reasons. And here, what changes is that we can do recursive decomposition. So we can represent the entire application from top to bottom by using this two-part task with continuation. But we are breaking local reasoning. Because the moment we are introducing continuation in there, we cannot properly reason about that thing. So it's kind of that hack prevents us from doing that local reasoning. And I'm not going to go into details here, but in general, it's a hack, so that breaks stuff. And that's the thing that it breaks. Single entry, single exit point, that kind of halfly is done. It has this one entry, one exit, but because of that hack, you're not always sure that that's the case. And soundness and completeness, we argued last year that that is true. So hope that makes sense. So tasks, either raw tasks and tasks with continuation, they fulfill the soundness and completeness, but they do not give us everything that structured programming can give us. So now it's time to enter the core of our discussion, senders and receivers. So when I say senders and receivers, I mean particularly this proposal, P2300, called STD execution. That's a proposal that it was supposed to go to C++23, but unfortunately didn't make it. So my hope is that it will be in C++26. And this proposal defines three main things: concept, an initial set of algorithm, and utilities. That doesn't define everything that we want, but it just defines the core elements. And I've tried to put a diagram to show how those things work. I'm not going to dive very deep into that. If you do not follow all these details, don't worry. We are not going to focus on how this will work. We're just going to analyze the properties that come out of that. So the first thing here, we define the concept of a scheduler which handles the computation resource. Thread pool, GPU threads, IO thread, whatever you name it. So it's something that represents a compute resource. And if you call schedule on that, you'll obtain a sender. A sender, what's a sender? It's something that describes a computation. Computation is a keyword here. I'm going to define it a little bit later. But you can think of it as concurrent work. One important part here is that the sender just describes this computation. It does not actually implement it. So it's just like an expression template. It describes what needs to be built, but it doesn't contain the code to execute that part. And again, important is senders promise to send notification when the work is done. So there's a standard way in which a sender or the work being represented by a sender can notify about its completion. The scheduler and the sender and the algorithms that that are built with senders are user facing, and there's a part that most users will probably not going to interact with. That's library internal, I'm going to go into that to see how this works. So the receiver is the part that gets notified when the work represented by a sender completes. So it's an asynchronous notification handler. If you take a sender and receiver and combine them or connect them, that's the proper term, you get an operation state. An operation state implements the details for a computation, right? So the sender describes the computation, the operation state actually implements all the logic for it, and the operation state needs to have the receiver, which is typically given by somebody else outside of the sender. So that thing is pretty important to understand this proposal. What we are going to focus on is the sender part. That's the main focus of the talk. If you don't know all these details, it doesn't matter. You can find more resources on that on the internet. I particularly enjoyed Eric Nibler's talk, two-part talk at CPPCon last year. So the fundamental part in these presentations is that senders describe computation. And what I mean by computation is any chunk of work that has one entry or one exit point. It doesn't matter how many threads that's executed, on which threads it's executed. It can be executed on CPU, on GPU, on other machines. It can be waiting, it can be whatever. If it's a chunk of work, if it has one entry and one exit point, then we call it a computation. And of course, we have some formalism, what an entry and what an exit point means. So let's look at some example. What computations are. A task is always a computation. It just happens to be on one single thread. And here I'm referring to raw tasks. Tasks over multiple threads. So if I have somehow a graph of tasks that spawn each other and then do some logic there, then they also can be represented as a computation. A group of computation is also computation, right? If you can have one entry point and one exit point to your group, it doesn't matter how you arrange them, you can still represent that as one computation. And also very importantly, the entire application can be a computation. It's just you have the main, which has one entry point and one exit point, right? Somebody calls main and you return from main, and that's your application. I'm ignoring statics and all the other stuff in there, but hope you get my point. So all that are computations. So any chunk of work, concurrent or not, that has one single entry point and one single exit point can be a computation. And let's look at one example, and I'm going to give you code on how you can implement that with P2300. So let's say we want to build this. We do something at the beginning, then we spawn 3 different things that can be done in parallel, and then we join, we do something else, and we continue. The entry and the exit may be on different threads. In my example, they're going to be on a single thread just because it's slideware, but they can be on different threads. So we have 3 functions, work 1, work 2, work 3, and we have something that combines the result. And this is the thing that describes the work that we are doing. We have a thread pool, so that's the execution context. We have a scheduler obtained from that execution context. And this is a sender. This sender, so you see this is a concept, this sender called work does a when all, so does the join of 3 different things. So this when all has 3 parameters. These parameters are looking the same. So we have a schedule of this schedule object. and then we pipe it to then, and we call this function work in it. So we describe what needs to be done here. This schedule function call describes the fact that I want to run this on that particular thread pool. And then this then describes the fact that I'm going to want to execute that work in the context that was generated by this, right? We have 3 of those in parallel. And here, at the end, we are going to wait on this sender to work. It will give me 3 values, and then I'm just going to continue with that. Again, you don't have to know how to read this code. That's not important. I'm just trying to familiarize a little bit you with the high concepts if you're not exposed to this previously. So if you would want to plot how this would work, if you want to plot a diagram of how the senders will, you would have something like this. So the when all sender contains 3 then senders which contain a scheduled sender in them. So all these nest together. That's how we describe senders. The completion of the sender is something like this. Sender always promises that the work that it describes calls one of these 3 things: set value, if it's a success completion with 0, 1, or multiple values; set error, if it's an exception or some other error type; or set stop, if somebody canceled that work before it reached completion. But in any case, no matter what, if you're starting the work of a properly expressed sender, you would get a completion notification, which is one of these 3. The receiver is, as you guessed, the thing that receives these things. So you can call set value, set error, set stop on the receiver, and the receiver knows how to deal with that. Typically, receivers are provided by the next sender that you're chaining into your work. And the operation state, as we said, is the combination or the connection between the sender and the receiver. Here we have, well, I try to express an object, operation state. The operation state object does not contain the sender object. It contains some implementation details. So it contains the implementation details for the work described by the sender, which will call one of these 3 APIs to the receiver. And the receiver is typically provided externally from the sender. So those 2 have nothing in common, right? The receiver is typically the next sender in here. So the operation state object needs to be alive during the whole duration of this. This is an implementation detail. The user typically do not have to be concerned about that. But the fact that the operation state is alive allows this framework to do a lot of optimizations, and you will get extremely fast code with this. So in the previous example, you don't have any memory allocation. Everything can be expressed just like if you express it with functions. So that's pretty powerful. Let's look at how we create the operation state. So I try to put everything on this diagram to show you the end result where we will go. So let's go over all these details. So we have the schedule logic, and we start from there. We put the receiver for the next operation together with this schedule object, right? So remember, the receiver is always provided by somebody external to the sender. In this case, because schedule was inside of then provides the receiver for schedule. If we put them together, we can have an operation state object. That's a simple C++ object, so that's a real thing. It's not just a concept. then somehow the then logic, the logic that's described by the then sender, will somehow contain this this object here, or refer to it, to the operation state. And this then logic will be coupled with another receiver. This time is going to be given by the when all, because when all calls the then logic. And by putting these two together, we find the operation state object. We have three of those because we want to do three in parallel. So we have three of these objects. This will be put into the when all logic, which will be coupled with the receiver. This time sync wait is the one who's providing the receiver for this. And with that, we put this into an operation state. And that's our final operation state. Now, let's look at how we start this thing. So when we start, operation state has only one operation. You can only start that. When we start, we activate the operation state object thing. Everything that you see in gray here is not yet activated. This one will activate the three operation states inside, which at their turn will activate the operation state within themselves. Then the operation state will actually invoke the logic that is described by the schedule sender. In this case, it will make sure that the computation will be executed in one of the thread pools. When that happens, it will send the completion notification to the receiver that is provided by then. And then the logic will no longer be active. So that's why I grayed it out. When the then receiver receives its notification, then we are starting to execute the then logic. At that point, we don't longer need the operation state for the schedule sender, so we can safely delete that if the implementation chooses to do that. We execute the then logic. Whenever we complete that, so whenever we actually execute the function that was given to then, we will call the receiver saying like, I'm done. And the receiver will do the same thing. It will inform the when all logic. And when the logic is informed by all three receivers that is completed, then it will just mark that, hey, I have the results from all the three parties. I'm now done. It will tell the sync wait receiver, and the sync wait receiver will report the values through our function call. And that's how you would execute the whole thing. Again, if this sounds a little bit too complicated, don't worry, it's not the focus of this talk. The focus of this talk is the fact that senders describe computation. I'll just show you how this is implemented, but the more important thing is senders describe computation. Okay, so we said that functions execute on the same thread, and for computations, we may have that the entry thread is different than the exit thread. And that allows us to use computation to solve concurrency problems. And that's important, right? You've seen in the previous example how we started on one thread, but then we just move through the threads to do that work in parallel, just to come back to the same thread. If we haven't used sync wait, then we could have used some other primitive, then we could have ended up the whole thing on a different thread. So if you look at it that way, the computations, which can be represented by senders, are generalizations of functions. And thus, we have here I would say the most important slide of the talk. Computations are for concurrency what functions are for structured programming. Computations can make concurrency be structured. And I'm just going to pause here for you to see that and reflect. Before we move to the next section, which tries to argue that this model is actually structured concurrency, are there any questions? I'm not saying anyone. If you have questions, please post them into a Q&A. I do have Discord open, but I'll probably not focus on that as much. So let's move on. So functions are for structured programming, and computations give us structured concurrency. And we argued that we can use senders to describe computations. So the main point is, how are we going to, that's what we are trying to show in this section, how senders can lead up to structured concurrency. Now, I do have some theoretical results. I've written a paper for the C++ Standard Committee, a very long one, and it's pretty boring, as you can imagine, trying to prove all my steps here. I'm not going to go into all the details. I'm just going to extract the summary out of there. But you can find the paper at this link, and you can see for yourself my proofs. So the first result that can be extracted from there: all programs can be described in terms of senders without the need of synchronization primitives. And that's important, right? So that is similar to the Wom-Jacobini theorem for structured programming. We can put everything in terms of senders, and we can structure the program that way. The next one is any part of the program that has one entry point and one exit point can be described as a sender. And by now, you should be familiar with that. I've repeated this several times over the course of this talk. So any part of the program that has one entry point and one exit point can be a computation, and we can use a sender to describe computation if we just make sure that we have the proper API semantics at the start and at the end. We should be good. And we can always adjust the API there to represent any type of work being done that we want to do concurrently to match this, this API schema. The next result: the entire program can be described as one sender. I'm going to show an example of that. That just gives us the start for our decomposition process. The next one is that any sufficiently large concurrent chunk of work can be decomposed into smaller chunk of work, which can be described with senders. That's the fundamental part of this thing. So we can represent the whole program as one sender, and for sufficiently large senders, we can decompose them into smaller senders. Actually, if you think about kind of everything can be decomposed, even small instructions, you can put them in senders. It doesn't necessarily make sense, but you can decompose stuff a lot. So hope that makes sense. And the final point here is not something that is a focus for our talk, but is still worth mentioning. The programs can be implemented using senders using maximum efficiency under certain assumptions. So, of course, it's a strange definition of how you would do that. You define efficiency in a context in which you're talking about all possible programs. But the key point here is that if you arrange the programs like that, then basically you're guaranteed to arrange the program in the maximum, in a state in which you can get the maximum work in parallel as you possibly can arrange them. So that's just worth mentioning. So the big takeaway from this, if I can summarize the takeaway from this paper, is that the computations fully encapsulate concurrency concern, right? So no matter what concurrent problem you have or sub-problem, you can always encapsulate that into computations. And that gives us brings us back to this important slide. Computations are for concurrency, what functions are for structured programming. So that's how we can use senders and computations to build structured concurrency. Okay, so what do we mean by structured concurrency? Well, just take the same principles from structured programming. Abstractions are building blocks, recursive decomposition, local reasoning, single entry, single exit point, soundness and completeness, and we apply them to our model. So let's see how senders and receiver stand to this test. Abstractions as building blocks. Well, we just said we're going to use computations, which can be described as senders, and those are similar to using functions. So all the arguments that structured programming makes for using functions to structure programs, you can just replace the word function with computations, and then you would get the same rationale for concurrent applications. So you can get you can get to the point in which computations are the building blocks, the abstractions that you need to build concurrent applications. Recursive decomposition, we just saw from those theoretical results that you can have computation that can be broken down into smaller computations, and you can use senders to describe that thing, right? So that allows you to build your applications senders from top to bottom, right? So if you remember the prime number example from which we took one problem and just decomposed it into a similar into smaller and smaller parts until we solve it, you can do the same thing with senders and receivers, and we'll have the example at the end to show that. Local reasoning. So nested scopes, I've shown you those diagrams, and you've seen that everything is nested in these proposals. So senders nest, operation states nest, receivers somehow nest, so everything nests, and you have everything that you care about is nested in that scope. And moreover, it's not just that, it's you encapsulate the local concerns. You don't care about how you're going to be called. Again, if you're doing your job properly, of course, you can always do hacks around that. But if you're doing your job properly, you don't care about how you're going to be called, how other parts of the system are working. You're just fully focusing on your part there. If we look back at our example, you can see that you just have the when all that just decompose into smaller problems, which never look back at how they are going to be used. In other words, there are no spooky action at a distance. When you're looking at work properly described by a sender, you do not have to think that, hey, maybe I have some other sender somewhere else that may interact with my stuff. If you've done your job properly, you can fully encapsulate that in there. All the concerns are handled locally, and the inputs and the outputs are clearly defined, right? So, and we have this nesting thing. That leads us to our next point: single entry, single exit point. Similar to a function, if we just put computation there, we have one single entry, single exit point. It's just the thread that the exit point is maybe different than the thread, the single entry. With senders, that's by definition, because we can start them just one way by starting the operation state. And the output of the work described by a sender is one of set value, set error, set stop. If we just think of them as one thing, we have only one exit point. By the way, you cannot have work that's been executed by a sender to call multiple of these. You cannot have both set value and set error, right? It needs to be one of them and only one. Not zero, not two, just one. In concurrent applications, there's often this style that's been used, fire and forget. You just start something. And currently, the P2300 has a way of doing that. It's an algorithm called start detach. You give it a sender and you will just start that sender, and you don't care about that. You have no control about the lifetime of that. That breaks single entry, single exit point principle. And that's why it's discouraged. I'm going to show you examples of how people may want to use this, but I'm arguing this is a bad thing to do. And currently the C++ Standard Committee is working on a paper to actually fix this thing. It's called async scope. That should make this thing disappear. I'm really eager to see that being forwarded to the committee. So all the computations have the same shape. They all started the same way. They all end the same way. So we do have composability on all that. That's how, similar to how we've done it in structured programming, we can do it in concurrent programming as well. Soundness and completeness. Basically, we try to ask the question whether structured concurrency can be applied or not. And the soundness is guaranteed because we can safely build senders we can build programs by describing them with senders, and we don't need to use synchronization primitives. And that's part of the theoretical results that I mentioned. And also, there's a completeness part in this. It's not just that we can build safe programs. All programs can be built this way, and they are guaranteed to be safe. Right? And with that, we basically checked all the items that we said we will have. And hopefully by now I convinced you that we can achieve structured concurrency by using senders and receivers. And now let's look at an example. Are there any questions before we go over the example? I see no questions, so let's dive into the example. So what we're going to do is we are going to build an HTTP server application that's going to be used for image processing. So for example, if you pass it an image, you can say, I want to cartoonify this image. So you can imagine different uses of that. Maybe you want some low-end device to be able to process image and you want to send that to a cloud or whatever. At this point, I have to mention that this is somehow overlapping with Dietmar's talk tomorrow. So I'm hoping that Dietmar will do a better job than I am in explaining the details of HTTP server and how you can build that with senders and receivers. The focus of this example is just to show you the points in the structured concurrency. It is not a walkthrough to senders and receivers, and it is not a walkthrough to how to build network applications with this. The fact that I'm using an HTTP server is just an example. So the goal of this example is to show that senders can be used as building blocks to do a recursive decomposition with senders, similar to what we've done with the prime numbers example, to show how local reasoning works, and to show the single entry and single exit point principle at work. And here, again, I have to apologize. I used star detach in a couple of places, and I'll explain why. Basically, we don't have that async scope proposal yet. There are some implementation, but they were not at hand for me. So those are the primary goals. I do have two secondary goals. We haven't talked about coroutines, and we know we can use coroutines to handle concurrency. I'm going to briefly talk about interactions between senders and coroutines. And also something that I find really interesting is how we can obtain type erasure with senders. Currently, the P2300 does not have the ability to type erase stuff. Everything is just templates. Of course, you're going to find the code on GitHub. So this is the link. This is the QR image for that. So let's get started. So the entire application is a sender. So I do have the main, and I'm just going to do a sync wait for something that's a sender. So I'm representing the whole work as a sender. You'll be seeing these arrows each time I want to point to specific senders if the example shows both sender and non-sender code. The get main sender can be expressed like this. I'm just going to start from something. This is a constructor given by P2300 that just says this is a sender that doesn't represent anything. If you start it, will just pass on yielding a value. Then you've seen an example with then, and here we're going to put the main logic in our example. At the end, we'll return 0 because we want to return successfully. This is the main thing, the main logic for our server. We create a static thread pool so that we can obtain a scheduler out of this. We can create an IO context that also represents an execution context. So you can get a scheduler out of that. We put some signal handler, and then we build another sender by putting it on the scheduler of the IO context. That's how you put it in P2300 by using on. There's other ways you can do that, but that's an easy way to do it for this case. And this function here returns a sender. That's why I put this arrow here. And this is one use of start detach. So this is bad, but in this context is not that bad because I kind of know the lifetime of this because I know the lifetime of this run. So whenever this run completes, I know this will also complete. But this is highly discouraged. You should not necessarily use this in your application. So let's look at the listener. The listener here returns a task of bool. So task is something that's provided by the P2300 reference implementation. It's a coroutine type. You can see that by the presence of this core return here. And a key point for this proposal is that you can go from senders to coroutines and back very, very easily. So you can mix the two things together and they work fine. Right, so listener returns something that looks like a sender, or returns a sender, however you like to put it. This is how we implement it. We have some listening socket. We have a while for accepting connections. Here we have one sender that just accepts connection. Then we have the logic to handle the connection. Now, the reason why I use a coroutine here is it easily allows me to represent loops and encapsulate them into something that's readable very easily, and still be still represent a computation, still represent something that can act as a sender. Right. So in here, I'm looping until the context is stopped, and then I'm just exiting afterwards. This is a sender. This is a sender that handles the connection. I'm not going to go into details what let value does. This is just a monadic bind to make sure that we have the data available for us for the entire lifetime of handling the connection. And then we have the second example of start detach. And I'm using this start detach as a simple thing to move ahead, because having one sender here, one sender here, so having two senders, and somehow I would want to continuously accept things while I'm processing the other things. So I'm just starting this handle connection on its own while I'm accepting new connections. And this is problematic. If you just look here, it's very problematic because you do not know the lifetime of this particular work that's been done here. So theoretically, you can destroy the whole application and this still not finish to its work. So that is problematic. It's not the case, but theoretically it's possible. This is just showing how async accept is implemented. Please know that it returns a sender. So that's the important thing I wanted to show here. This is the handle connection part. So this is a sender, and this is how you typically would use multiple P2300 algorithms to describe your work. So the first thing you'll do, you're going to read the HTTP request. This is a function that returns a sender. Then you're going to transfer the result of that function, which is an HTTP request. You're going to transfer it to the pool of threads. So you're going to transfer to this scheduler. You don't want to block your IO thread while you're executing your logic. Then you're going to actually handle the request here. Again, let value as a monadic bind. Then if somehow this fails with an error, or whether it's canceled, then we have this function here that again returns a sender, just 500 response. We just it's a sender that just returns a 500 response. And then at the end, we have a response, and we call this function that returns a sender. So again, this is the monadic bind. That's why we are allowed to return something that returns a sender, in which we pass this result, and that would be transferred to the caller, the user who is using this service. With just 500 response is a pretty simple implementation. We create an object, and we just use this just function to return that object. So this is a sender that just returns this value, doesn't do anything. Read HTTP request is also a sender, or something that behaves like a sender. It returns a coroutine task type. And because I'm not guaranteed to be able to read the request in one go, I may have a while, so I'm using the same pattern here, and I'm going to use this async read. This is my only other sender in this slide. So we look one level down for it. So I haven't stopped in my previous example, but you can see here how if this returns a sender, you can co-await that sender to return the value and then just do your work. You do this in a while or whatever, and then at some point you return, right? So everything that you return here as a coroutine can be used as a sender. And if you have a sender, you can co-await it in a coroutine. So there's a nice integration of the two features. That's really nice. Just to point out, typically how you would implement coroutines is not as efficient as if you would use the P2300 functions. So that's the difference. That's why sometimes I prefer to use the functions. Sometimes I don't care about that. I'm just going to use these nice features. Moving on, async read returns a sender, as I said. And let's pause here for a moment and see what this sender means. So I said computations are describing any type of concurrent work. Well, the reading mostly is being waiting on some data on the network. So mostly you're not waiting here. You can extend the notion of work to the party that's on the other side of the socket sending data to you, right? So you can use computation to express work that's been done on some other computer that somehow interacts with you, right? You can represent with senders computation that do CPU intensive work, GPU intensive work, or simply waits. And that also applies to this read HTTP request. This mostly just waits. It doesn't necessarily do a lot of work. So that's, I think that's an important thing for us to remember. Write HTTP request is similar to read HTTP, sorry, write HTTP response. there's a typo here, sorry about that. Is similar to read HTTP request. Again, it uses a coroutine. It uses some iteration. In this case, I have two loops, and I'm using again another sender as my base. This is how async write signature looks like. So I'm returning a sender. This is how handler requests, we finally come to the core of it. So we looked at reading, but writing the core it can be done with something like this. And again, I'm using a coroutine type here, but I'm using it now for a different purpose. Here, I'm using it to do type erasure. So senders are all templates. If I'm returning a sender here, it needs to be a clearly defined type. But because I'm using different types of senders to implement this logic, I need somehow to bring all those smaller senders to one single type. So I need some kind of type erasure. And a very easy way to do that is by using a coroutine here. It may allocate memory, that's a small price that we have to pay, but it's, I wanted to show how this is done. I'm not going to go into all of these things that return coroutine. So everything that you can see here, co-return, that's something that, this is the only, this one and this one is the only coroutines here. These are normal function. So I'm having this that returns a sender. I'm awaiting the result of that, and then I'm co-returning the result of that. So that's an interesting pattern when you want to just chain computation like that. So I'm going to look into handle cartoonify. That's the implementation. I'm not going to go over what it does, but essentially the big part is that I want to start two different things in parallel in two different threads, if I have the threads. And then I want to, when they both complete, I want to join them and apply something else, and then I'm going to send the result, right? So I'm not using senders just to describe the I/O parts of this and the handling. I'm also going to use that to parallelize the work that I want to do. So in this example, what I've shown is that you can use recursive decomposition with senders or with their coroutine substitutes. And that's all the functions that we have visited, and they were either returning senders or they were coroutines. So get main sender, which calls listener, which calls async accept and handle connection, which calls read async connect, handle request, just 500 response, write HTTP response, and so on, right? So the same pattern that we've seen while trying to solve the prime numbers applies here. We can use this recursive decomposition. And I hope that, that this walkthrough of this example shows you that indeed the same principle that applied there apply here for structure concurrency. One thing that I haven't properly stressed out is if you look at one of these functions, you never care about what the other parties are doing. You're just going to focus on whatever you're handling in that particular function or coroutine or computation, however you want to look at it. You don't care about the external world. You don't have any interactions with the rest of your application. So you have local reasoning here. And that concludes my example. So let's just dive into conclusions. So for 57 years, since we started to talk about concurrency in software engineering, and we started to talk about concurrency before we formally had software engineering as a discipline, concurrency is still not a solved problem. We've solved most of the problems in software engineering in a very short amount of time, but concurrency seems to not be solved. This is a model that can be used to solve concurrency, right? So what we did, we took the lesson from structured programming, we applied to concurrency problem, and we arrived at structured concurrency. Senders and receivers are not the only abstractions that can solve this. So any language that has a sync await, you can reason about the same thing, that it has structural concurrency. Senders and receiver, this proposal has this nice effect that you can implement them efficiently. The key insight for the talk is that you use functions for structured programming as your fundamental building blocks in the same way you use computations as a fundamental building blocks for structured concurrency. And structured concurrency is about these 5 things: abstractions as building blocks, recursive decomposition, local reasoning, single entry, single exit point, soundness and completeness. And with that, I conclude my talk. Thank you very much.